I managed to record a whole lecture in pre-calculus on mute. Facepalm emoji. Okay. So I meant to run this by you guys last day, but then I forgot. I scheduled the lab exam. Remember, the lab exam is not going to be in Excel, right? It's just going to be print out 30-ish multiple choice, essentially the short answer part of the final exam, definitions, right? If you see this, then what does that mean, right? That kind of stuff. And so I've scheduled it for your labs on April 3rd, on Friday, April 3rd. The reason we actually have a free lab the week before, so we could do it on the 27th, March 27th, and just be done with all the labs, get it over with. But the reason I didn't do that is because we've got our test 2 on the Monday of that week. So I want to kind of gauge, since you guys showed up, you get a vote. What would you prefer to do? And so either the 27th, have a kind of a really tough stats week, really heavy stats week, or spread it out across the 2 weeks on April 3rd. So I'm going to go for March 27th, just by show of hands. Okay. It's looking like it might be a 50-50 split here. How about April 3rd? Hey, everyone's entitled to their own opinion. Okay, so that's pretty tough because I'm seeing roughly 50-50 split. I'm going to keep it on April 3rd, but the 27th you'll have kind of time to review for the final exam in the lab, right? So, or wrap up lab 8, which will be your last lab. So we'll kind of use that as a spare day. So we'll keep the schedule as it is, put it off till April 3rd. So, okay, good. Did everyone get a probability handout? I guess I need a probability handout. And if anyone's on here, hey Sage, I forgot to post it on Moodle because it was just this morning. So you'll just have to follow along. I'll post them after though. Let's see if I can find it. When did I teach? This stuff. Chapter 2. What? Oh man. Okay, you know what? Sorry, just have a nap or something. There. Okay. My iCloud. Oh, it did update. Nice. Oops. Doesn't help if it's not on here. There. Still called chapter 2 notes, but I'm just going to erase this. Stat 121. January what? 29th? Oh my goodness. 2020. I almost wrote 2019 still. That's not as bad as last year. Pretty sure I wrote like 2015 or something. I don't know what happened. Okay, so, haha, I almost forgot. We didn't quite wrap up regression last day. So before we head into those notes, another reminder, labs this week will be to finish lab 3. And Jenna Downey will be in C286, 268, 286, I think, for both labs. Right, so we've talked about that before, so I'm just gonna leave it. But if you're not sure what I mean by that, just ask me. Okay. So we finished simple regression last day, and we talked about how do we calculate the slope, how do we calculate the intercept. Pretty sure. Did we finish? Oh yeah, we talked about outliers. Right. What did we talk about? Yeah, we did get there. It's all a blur. Yeah, we talked about outliers. Essentially, if you have an outlier or you think you have an outlier in your data that you think might be pulling your line of best fit, what you do is you pull out that outlier temporarily, right? Fit the model and see what changes happen. And then if there aren't huge changes, I would opt to put the data point back in, right? Because we always want to push to keep as much data as we possibly can, right? And so I remember talking to a friend of mine in grad school, and she was in biology, and so she was like drawing blood from mosquitoes. I know, irony, right? Like she was doing something with mosquitoes, tiny itty bitty things. And so, and then she recorded data, of course, and then she's telling me, oh yeah, my analysis, it's going great. I had like 15 points, but like that didn't work, so I just deleted them. I was like, okay, shouldn't do that. So don't do that, okay? Try to keep as much of your data as you have, or as you can, and go from there. Okay. We're just going to touch down in chapter 4, which is on multiple regression, before we head into chapter 5, which is on probability. So multiple regression, there's just the one section. 4.1, an introduction. Introduction to multiple regression. So far, right, simple regression was when we have one X and one Y, right? We have one predictor variable or one explanatory variable X. It's reasonable to think that, well, there could be more than one explanatory variable, right? The response doesn't hinge on one thing and one thing only, right? And so multiple regression just makes room for multiple explanatory variables. Okay. So simple regression just has one explanatory variable. Explanatory variable. Oops. The explanatory variable, we could also call it a predictor. So sometimes I'll throw that out there, predictor. So it has one explanatory variable, X. Okay. Multiple regression. allows for more than one explanatory variable. Allows for more than one explanatory variable. So we call them x1, x2, x3. X sub k is usually what we do. So now, instead of, so in simple regression, we had y hat equals b0 plus b1x. Right. This was our model. We figure out what the slope is, what the intercept is, bless you. And then we use that model and we plug in values of x and get the predicted value of y. For multiple regression, it's going to look similar. There's still going to be an intercept, and then each of these x's is going to have its own slope, right? This is going to be hard to visualize in your mind, right? Especially more than maybe two x's. Very difficult to think about, right? But for each little x that we put in, right, it's going to adjust the slope and adjust the line, right? And so b1x1 plus b2x2 plus b3x3 all the way up to allowing for bk x, oops, xk. Bless you. Oh. I'll scoot up here, right, and add after my xk, just so you know, k predictors. Or k explanatory variables. Just leaving room for as many as you could possibly want. Yeah. Usually we tap out at 2 or 3, right? There's usually no need to have more than 2 or 3 x's in there, right? But the model itself, it just allows for as many as you want. Yeah, so what this means is, well, we're going to have to find essentially a slope for each of these x's. That is not something that we're going to do by hand, right? So this is purely Excel or whatever software you're using. It's a job. Okay? And so we do not find B1, B2, B3 up to BK, oops, by hand. We use software such as Excel, but honestly, if you're doing multiple regression, you're probably a little bit more advanced in stats, and so you would use something like R, which is a programming language, but and way more powerful for statistical analyses, right? Or there's even a click, click, click option, SPSS. So all these are, statistical softwares, but Excel is the one we're using. Right? So just be aware that it exists, but we're using Excel. Okay? So as a quick example, right, if I tell you that y hat is 4 plus 3x1 plus, or sure, minus 2x2, made my plus into a minus, that works, plus 14x3, find the predicted value of y when x1 equals 1, x2 equals 4, and x3 equals 2. Whatever those things are, right, all we do is just plug them into the equation, right? So then y hat is 4 plus 3 times 1 minus 2 times 4 plus 14 times 2. My predicted value of y, right, y hat, is then 4 plus 3 minus 8 plus 28. So my predicted value of y is 27. So you use it the exact same way that we did for simple regression, right, where we just have one x and we plug it in and find the predicted value of y. Now, I just have multiple x's, but I tell you what they are, and then you just plug them in and calculate it. The output that we'll have a look at is a little bit, well, it's not too bad. Let me see, let me hope that I actually did a little squiggle here. I don't think I did. Maybe. So I'm stealing this example, the Mario Kart data, just because we're going to do an analysis on it. So it is from your textbook, of course. And in a second, I can tell you what page it should be on. 83, if you want to look. And so if we just go back here and we have a look at the description, and so it's pretty sure it's eBay auctions for Mario Kart, something or other. Here's the funny part about stats is I usually don't really care about what it's about, right? Sometimes it's helpful. Usually it doesn't really matter that you know too much about it. So that's why I think it's so funny where if someone tells me that they do health statistics or they do biostats, which shouldn't those be the same? Oh, anyways, so there's all these kind of econometrics. So usually if it ends in metrics, it's statistics, right? So econometrics is economic statistics, right? Biometrics, biological statistics, right? So, but all of those things, we all draw on the same concepts. So we should be able to deal with any kind of data. But anyways, here's some eBay auction, whatever data. So we want to try to predict the price, and some of the other explanatory variables that we have is whether the condition is new. And so it's just been coded as a 0 or a 1. It's going to be a 1 if it's new and a 0 if it's used. Right? And so sometimes we just have these two options. That would be a categorical variable, right? Even though we're coding it as a number, but that's just because numbers are easier to deal with. Stock photo, again, is just coded 0, 1, right? And so it's a categorical variable as well. And so if it was a stock photo or if it was a real photo of the item. Duration is the length of the auction in days, taking values from 1 to 10, right? So the length of the auction. And then the wheels, the number of Wii wheels included with the auction. A Wii wheel is a plastic racing wheel that holds the Wii controller and is an optional but helpful accessory for playing Mario Kart, apparently. So I thought that was pretty cute. So, so anyways, if we're looking at this, right, we wouldn't say, oh, price would depend purely only on the wheels, right? I just need to look, how many wheels are there, and I'll be able to know what the price is, right? That's pretty unreasonable. And so we would say, well, it might depend on all of these things, right? And so that's when we would stretch it to a multiple regression, right? To allow for all of these things to be in our model. So if we do a little hand wavy stuff, blah, blah, do you guys know hand wavy stuff? Like, oh, nothing to see here. We get a model and it looks like this. I'll keep the table name so you know where it came from. This is from page 85. So eventually we fit the model. Whoop, wants to be on this same page. There we go. What you've seen in the lab looks pretty similar to this table, except you just have the intercept, right? And then the slope, right? And so we just have the intercept and the slope, and then we didn't have these lower three values, right? But now we have the exact same thing. So we've got the intercept, right? And then we've got a slope for the condition, whether it's new or not, a slope for the stock photo, a slope for the duration, and a slope for the wheels. And so now we can take this, ignoring everything else, because that's for another course, which confusingly, I am teaching right after this. So anyways, ignoring everything else, now we can write out our model just like we did with the simple linear regression. And so now we can say, okay, well, in general, y hat, which is our price, so maybe it's more helpful if I write price hat. Right? Anything with a hat on it in regression is a predicted value. So the predicted value of price is going to be, well, the intercept 36.21. Let's round to 2 decimal places. Make a note here. Rounding to 2 decimal places, just because I'm lazy. 36.21, that's our intercept, plus 5.13 times the condition new. Right. That's your x1. Plus 1.08 times the stock photo. Now we've got a negative slope, right? Which tells me what? The positive slopes tell me that for each increase in condition new, right? So if it's new, the price is higher, right? Than if it's used. That's fine, that makes sense. The stock photo, it looks like the price is higher if it has a stock photo. Is that what it was? Stock photo? 1 if the primary photo was a stock photo. Okay. A little bit higher price. Maybe because they look nicer. But now we've got a negative slope for the duration, meaning that predicted value of the price is going to decrease the higher the duration is, right? So for each increase in the duration, right, the length of the auction, the predicted price is going to decrease a little bit. And then for the wheels, oh, it goes way up, right? Must be a helpful tool. Right? And so we get minus 0.02, oh, sorry, 0.03. Forgot we were doing 2 decimal places. Times the duration plus 7.1 0.29 times the wheels. Or we could write it just simply as y hat is 36.21 plus 5.13 x1 plus 1.08 x2 minus 0.03 x3. Gotta scoot this over a bit. Should have known. Plus 7.29 times, oh, I almost wrote wheels, x4. Whichever way you want to write these is fine. All right. So now, if I asked you, okay, well now I want you to predict the price of, what is it? If it's used, so predict the price four observations from the final auction price. I'm trying to figure out what the thing is. Mario Kart, I guess. I don't know. Some sort of Wii thing. I don't know. Predict the price. I'll just say if the unit is used, has a stock photo, the auction is on for 4 days and has 2 wheels. In terms of our variables, right, I'm saying that x1, right, the unit is used, and so we can say that the con new, which in the other model is just x1, well, that's going to be 0. It has a stock photo, so the stock photo variable, which is x2, is going to be a 1. The duration, which we can also call x3, is 4 days. And the wheels, which we can call x4, is 2. Okay. So now, knowing what these things are, we can plug them into our equation, right? We can just churn out the predicted value. So we had, where was it? Y hat, and I'm going to keep the simpler model. I'm going to cheat and steal it because you probably have it on your same page, but my page is really small, so I'm just going to copy. So now I can say that y hat is 36.21 plus 5.13 times, oops, 0, plus 1.08 times 1 minus 0.03 times 4 plus 7.29 times 2. I don't have these pre-made, so here we go. Y hat, I'll just start this on the next page here. Y hat is 36.21 plus 0 plus 1.08 minus, oops, 0.03 times 4, 0.12 plus 7.29 times 2. Of course, we should be using all the decimal places, but like I said, I got lazy, so that's okay. 14.58. If you're doing it in Excel, right, you can just click on the cell and steal the whole thing, so it's a lot easier. And so we get 36.21 plus 1.08 minus 0.12 plus 14.58. So the predicted price I get is $51.75. Phew, came out reasonable, I think. Not that I know what we're selling here, right? But that would be our predicted price for this particular unit. We understand that that's not necessarily the exact price, but based off of our model and our other data, right, that's where we would predict this thing to be at. Right? Nice. And so the last thing I want to talk about in multiple regression is that for simple regression, we used R squared to try to figure out how good our model is. In multiple regression, we use the adjusted R squared instead. And so, and I'm pretty sure it just will give you that in the output. I have to play around with it, but it should just give it to you in the output when you do it. So in simple regression, we use the R squared as a measure, as a measure of how well our model fits the data. Remember, R squared is a percentage. And the closer it is, closer to 100, is best, right? So if the R squared is 20%, that's pretty bad, right? You want to get as close to 100 as you can. 100% R squared means that every single point is on the line, right? Just like the correlation of 1, every single point is on the line, right? And so you want to have a high R squared, but we also kind of said that, well, it depends on the data, right? It depends on what we're talking about. Sometimes we're not going to be able to rein it all in, right? So then our R squared isn't going to be as solid. But as close as we can get to 100, that's good. Anything over 80, I would consider good. Right? And so any R squared over 80% is typically considered good. So like I said, in multiple regression, we use the adjusted R squared. Maybe I'll capitalize the A in adjusted. The adjusted R squared instead of R squared. Oops. But all we need to know is that the adjusted R squared behaves the same way, right? So a high R squared, that's good, even if it's adjusted, right? But the adjusted R squared behaves the same as R squared, right? So high is good. The adjusted R squared is just to kind of rein it in, because the more predictors, so the more X's that you add into your model, the higher R squared will be. Because with every additional explanatory variable that we throw in there, right, our model will get better. But the adjusted R squared just penalizes you a little bit for having too many variables in there, because we want to have as simple of a model as we possibly can. And so that's what it's doing in the background. But all we need to know is for the multiple regression, we're going to use adjusted R squared instead. But it behaves the same way. Nice. Okay. Phew, I nearly forgot about multiple regression for you guys. It's the end of chapter 4. Blink and you miss it. Into chapter 5. So chapter 5, we've got that handout. I know it gets confusing, right? And this was to save us some writing. I apologize because I had these typed up from a few terms ago, and then I haven't really gone back and edited them. Have you guys ever thought about how you say edited it? I edited it. I edited it. I know, try it. I edited it. Doesn't make sense. Anyways, I did not edit it. So here we go. But I read through it, it's fine. The spacing though leaves something to be desired, okay? Basically what I did was I typed up my notes that we would have written up in class. Here they are, right? And so we'll go through and just kind of save ourselves some writing. So chapter 5 is going to be on probability. And so I'll just call this probability, which gets confusing later on because we're going to be talking about probability in all the following chapters, but this is the only chapter that I'll call probability. I know, because this is the only one where we actually have to calculate probabilities. Right? Later on, we'll talk about probabilities, and from the normal distribution, we'll get probabilities, but this is the only section that I'll call probability. And I'll say this right now. This is one of those sections that we just need to get through. Right? We need to do it. We need to talk about it. I'll prepare you for the final, and then we'll get on to more interesting things. Right? So, yeah, this course we get to introduce you to everything. We don't really settle down on one thing, which is annoying, but we all understand probability, right? And so, but now we need to talk about, well, how do we calculate probabilities? How do we deal with probabilities? How do they interact with each other? And so a probability is just a proportion of the times that something would happen if you repeated an experiment or if you completed a trial essentially an infinite amount of times. For example, if you flipped a coin an infinite amount of times, you would end up with a 50-50 split. Right? Turns out it's a 51-49 split, but anyways, doesn't matter. We're gonna assume it's 50-50. Okay? Same thing, you roll a die, right? These are all what we call random processes. So a random process is just anything, any process that's going to yield a random outcome. Right? And so if we roll a die, for example, that's going to be a common go-to, then I can get either a 1, 2, 3, 4, 5, or a 6. Just assuming a 6-sided die. If I flip a coin, I have 2 options. right? And so for all of these, what we think about is, well, if things are random and if everything is good and fair, right, then each of these is going to have an equal probability of happening, right? And so here, I'll say each outcome, oops, has an equal probability of happening. So if we've got a list of all the possible outcomes, we call that our sample space, and we denote it by a capital S, right? And so, and usually we use set notation. And so if we've rolled a die, then our sample space is the set. So we use curly brackets, 1, 2, 3, 4, 5, and 6, end curly bracket. Set notation is not something that I need you to know, just be comfortable reading it. So that's why I want to introduce it, right? So if you see something in curly brackets, well, that's just going to be a set of outcomes, right? And so if you've rolled a die, then your sample space S is 1, 2, 3, 4, 5, 6. No matter what happens, if you roll it, the outcome is going to be one of those things. Okay? So we're going to use probability notation. Let's see if I can highlight some things here. So the probability of A, we usually just write, instead of always writing the probability of A, the probability of rolling a 4, for example, we would say just capital P and then of A. And this is going to be true always. If I've got something on the outside, right, that's the name of whatever I'm doing. And then inside the brackets, I just read it as of, and then whatever is inside the brackets, right? So P of A, right, the probability of A. Okay. Or P of A. It's fine too. Sometimes we'll be able to talk about if we know the outcomes, right? If we know the potential outcomes, flipping a coin, for example, we know that there's can be a heads or a tails. And so then we can say the P of H is 0.5 and P of T is 0.5. Even by context, right? P of 2 is 1 in 6, right? Then I'm saying the probability of rolling a 2 if I roll a die, a 6-sided die, is 1 in 6, right? And so let's talk about some probability facts. Okay. A probability has to be between 0 and 1, right? So it's going to be a decimal between 0 and 1. 1 meaning that it will happen 100% of the time, right? 0 means it'll never happen, right? There, I did it. I pulled in this and I didn't even think about it. A probability is a proportion, and a proportion can be multiplied by 100% to get a percentage, right? So that's why I've got approximately equal to a percentage, right? But all these 3 P's, probability, proportion, percentage, are essentially all the same things, right? So we can use them interchangeably. So these 3 can be used interchangeably. Just remembering that the percentage is 100 times the proportion or the probability. Right? But often we talk about the probability of this happening. So the probability that I ace this test is about 70%. You also know by me saying that, what's the probability of me not acing this test? Must be 30%, right? So we already understand that probabilities add to 100 or 1. And so the next fact is not that crazy. So the total probability in your sample space, right? So of all the possible outcomes, if I boil it down to 2 possible outcomes, right? I ace this test or I don't ace this test. Well, that's my sample space. So the total probabilities have to add to 1. So on your formula sheet, these things are on there. Okay. Where's your formula sheet? And I've got extra formula sheets here still if anyone needs them. Yep. Starting with rule number 1, P of A is between 0 and 1, inclusive. And then on your formula sheet, it actually has for any event A. And then the probability of the sample space, so meaning looking at all possible outcomes, that total probability must be 1. Right? So this is saying total probability must be 1, which is exactly what we said in words, but I just want to emphasize it, right? Because it's new notation, right? Probability notation, set notation, whoa. But as long as you're comfortable reading it, right? I don't need you to be so comfortable writing it. That will come naturally because you'll get lazy. And so that's how we develop this, is because we get sick of writing. The probability that this happens is this, right? Nice to have just shorthand for it. But if you want to just write it out in words, I'm fine with that, right? So being able to read it is one thing, being able to write it is another thing, right? I want you to be able to read it, understand it, not necessarily write it. Although you will get there, I promise, if you have to write it out a bunch of times. Any questions so far? Okay. Then let's talk about some terminology, right? So we say that 2 outcomes are disjoint, or usually I've heard a lot of people, like just in life, people say, oh no, those 2 things, they're mutually exclusive, right? What does that mean in terms of probabilities? Well, if they're disjoint or mutually exclusive, those 2 things mean the same thing, right? And it just means they can't happen at the same time, right? So their shared probability of happening is 0, right? And so if they cannot both happen at the same time, something happened up there, but I didn't see it. Anyways. Oh well. We'll come back to events that are disjoint, right? But we just keep in mind that the probability that they happen together, just zoom in a little bit here. The probability of the events happening together, or happening, together, let's say, is 0. Okay. So less important is the events, An event is a set of outcome, or it could just be a single outcome. But usually if it's a single outcome, we just call it an outcome. And so not terribly important, but an event, we'll talk about events, right? Usually I don't care about just one thing happening. Let's say that if I'm rolling a die and I don't really care if I roll a 4 or a 6, right? Let's say I'm betting and I put money on 4 and 6. I don't really know how betting works, but anyways, that's what I'm doing. That's my game that I'm playing, right? I bet on 4 or a 6. So then I don't really care whether I roll a 4 or a 6. And so then we can say, well, I'm going to denote that as the set B, right? So usually I use capital letters for events, right? So the set B is the event of rolling a 4 or a 6. So in probability notation, we can break this up, right? And we can say, well, I know the probability of rolling a 4, and I know the probability of rolling a 6, and they're both 1 in 6 because these are just the outcomes, right? Only one is going to happen for each roll, right? And so I've got a 1 in 6 chance for each of these rolls, and it doesn't matter if I'm looking at a 1, 2, 3, 4, 5, or 6, right? They're all equally likely because we've got a fair die. And so what we can write is that the probability of B is the probability of 4 plus the probability of a 6. Those probabilities are going to translate to actual values, right? So 1 in 6 plus 1 in 6, we can just add those up. We've got a common denominator, so 2 over 6. Disjoint events are not that interesting and not that common, right? It's more common that we have events that are not disjoint. And so if we think about a deck of cards, right, our kind of usual gambling thing, deck of cards, right, now we have to deal with something a little bit more complicated. But if we think about our whole deck, right, we've got 52 cards in a deck, and I printed it out for you just so you have it in front of you. Hard because I didn't print it in color. You should maybe know. Maybe make a note to yourself that the bottom 2 rows are red, the top 2 rows are black. I've had students before kind of talk, I don't know what a deck of cards looks like. How can you expect me to know what a deck of cards looks like? Well, here, I'm giving it to you, right? We don't have to know. But just some things to keep in mind, right? There's 4 suits. I can never remember really the names of the suits because I always want to call those clovers, but I know that's not right. Clubs, maybe. Actually, let's look at shuffle. So and then hearts and diamonds, right? So I'm not very good with cards either. So if you're feeling like, whoa, that's way too much and that's not that, it's okay. Figure it out. These are all face cards. So they got a face on them, right? And so if we let the event F be drawing a face card, right? Then I've got all of these face cards to choose from, right? So if I ask you, what's the probability of drawing a face card, knowing that the total number of cards is 52, right? The probability of drawing a face card is 1, 2, 3 times 1, 2, 3, 4. 12. Or you can count that. 12 out of 52. So then what we can say is, I think I have it underneath, so I'll just leave it so I can see it. the probability of F is 12 over 52. You can use your calculator, but now you know the probability of drawing any face card from a full deck. If we let the event D be drawing a diamond, so now we're talking about all of these cards, right? Now we've got 10 plus 3, 13, right? And so we've got 13 diamonds, you can count them out if you want. So 13 cards satisfy being a diamond. And so now I've got these diamonds. What if I asked you, what's the probability of drawing a diamond or a face card? Now, we could count them out, right? How many cards satisfy being a diamond or a face card? But the glitch is this overlap, right? These 3 diamond face cards, if we just added up our individual probabilities, we would be counting these 3 twice. Right? And so to find the probability of a face card or a diamond, what we do is we take the probability of a face card plus the probability of a diamond, and then we subtract the overlap once, right? So we decided that the probability of F and D is going to be 3 over 52, right? And so we can subtract that overlap to kind of smooth it out. So I imagine it looking like this, right? And so when I subtract that overlap here, then I smooth it out and I'm kind of on the same plane, right? And so this is the addition rule, the general addition rule on your formula sheet, which I should have here. So this gives rise to the general addition rule for non-disjoint events. Oh, you know what? This is on your formula sheet. Let's just think about for a little bit, right? Back to disjoint events. Disjoint events, we said, well, those are 2 events that would never happen together, right? For example, in the card situation, we still have disjoint events, right? The probability of drawing a diamond and the probability of drawing a heart, right? If I'm drawing one card from a deck, it's either going to be one of those, there can never be both, right? And so those would be considered disjoint events. And so if you've got disjoint events, the overlap is none, right? And that's why initially when we were talking about the probability of rolling a 4 or a 6, we were just able to add those 2 probabilities together because the probability of a 4 and a 6 was 0, right? Because they're disjoint events. And so then you can just plug in 0 for the probability of A and B, right? A and B being just whatever events you're interested in. And so that's why it's the general addition rule, because we can plug in the special case of having disjoint events as the probability of A and B is 0. I'm having a panicky moment and I think I'm not on mute. Okay, good. That's gonna haunt me for a while now. I better not be, because there's a lot of blabbing going on here. So better not be on mute. And so here, if I know, right, if we count these things as 1 thing, 2 things, 3 things, 4 things, as long as I know 3 out of the 4 can be any 3, right? Doesn't necessarily have to be the probability of A, probability of B, the probability of A and B. right? As long as I know 3 of these out of the 4, right, I can solve for the 4th one because I can rearrange and I can solve for it. Right? So usually these problems are going to be, okay, so the probability of A happening is this, the probability of B happening is this, and the probability of A or B happening is this. What's the probability of A and B, right? And then hard part is being able to read the question and say, that's probability, that's the event A, and this is the event B. Right? That's the hard part. The math is not so bad. Right? So I've got examples, don't worry, but they're kind of a little bit later on because I smushed them all together because there's a couple of other things I want to talk about. Then we'll do a couple of bigger examples. Probability distributions. A probability distribution is a list of all the possible outcomes, right? So all the possible outcomes, that's your sample space, right? And so up here, this is your sample space. Up here. And in this example, we're kind of kicking it up a notch and saying, well, now I'm rolling 2 dice, right? And now I'm looking at the sum of these 2 dice, right? The lowest possible sum that I could have is 1 + 1, right? If I have to roll 2 dice at the same time, and then I'm looking at the sum of them, right? And now we get a more interesting probability because it's going to be 1 in 36, right? Highest sum that I could get is 6 + 6, so 12, and then all the possible outcomes in between, right? There's a couple of different ways that we could get, well, 7 has the highest probability, and so if you think about, I don't really gamble, but I'm pretty sure by this, a 7 would not pay out as much as a 1 or a 12. Right, which makes sense because there are a lot of different ways that we could get a 7, right? Could be a 6 and a 1, 1 and a 6. What are those different? Sometimes, right? Depends. Depends what we're talking about, right? 3 and a 4, 5 and a 2, 2 and a 5, 4 and a 3, right? And so it can happen in lots of different ways. So here down below, right? Just like it says, it's got the probability of each of these events happening, right? And so we see that, okay, well, 2 and 12 actually have the same probability because, well, the dice don't really care. 1 and 1 has the same probability as 6 and 6, just as rare. And then probabilities increase until they get to 7, and then they So this is a probability distribution. So it's a table, all the possible outcomes, and then each of their probabilities, individual probabilities below it. Pretty common question is, what's a valid probability distribution? So a probability distribution has to satisfy 3 things. Okay? So the first thing is that all these outcomes that are listed here have to be disjoint, right? Because in order for them to have their individual probabilities, right, I have to be talking about disjoint outcomes. That's the first thing we have to check. We know probabilities have to be between 0 and 1. Right, and so that's true for probability distributions as well. So you're going to scan usually you're given, a table of different options for probability distributions, and then you have to pick which one's valid. So then you scan the table, see if any values are not between 0 and 1. Those are out right away. And then, of course, the last one, again, going back to those probability facts, right, the total probability has to be 1. Right? And so if you add up all these probabilities, we have to get to 1. So if we have a look at this little example here, if we've got distributions, so probability distributions for household income in the United States, only one of these is a valid probability distribution. So we're going to go out and figure out which one it is. So first thing we have to check, right? These groupings have to be disjoint, right? This one stops at 24, so this is 1,000. Stops at 24, picks up at 25. So far, so good. 49 to 50, okay, no overlap. 99, 100, still no overlap. So these are disjoint outcomes. And I've talked about it below, so hang tight. Next thing we have to check is that all these probabilities, or a valid probability distribution, probabilities have to be between 0 and 1. Right, all of them. So we can scan through here, all between 0 and 1. Here's a negative. So B is out. Right, B is no longer an option because we've got this negative probability. But then the rest are all looking good. So now it's between A and C. So now we can add these probabilities. So first, so option A, 0.18 plus 0.39 plus 0.33 plus 0.16. I get a sum of 1.06. So that's bad. We already know it can't be a probability distribution or a valid probability distribution. 2.28 plus 0.27, doing the same thing for the next one, plus 0.29 plus 0.16. Right? And so, and I'll do a little. So C is the valid probability distribution. So usually you'll be given a table like this. You have to figure out which one's a valid probability distribution. And it just hinges on the probability facts, right? Have to be disjoint between 0 and 1 and have to add to 1. Any questions about that one? Or so far? Then let's talk about the complement of an event. Oh, fun to say. Complement of an event. We already talked about the complement, we just didn't call it that. So the complement is just going to be the opposite of whatever we're talking about. So if we go back to the set B, where B is rolling a 4 or a 6, the complement of B is rolling anything but a 4 or a 6. And so when I said, oh, the probability of me acing this test is 70%, you know the complement, right, is me not acing this test, and you know the probability of it is 30%, right, because there's only 2 options here. And so the complement, the probability of the complement of A, and usually I try to be careful and do a superscript C, because complement, but sometimes I'll kind of revert to old habits and just use a little prime, and so a little kind of apostrophe. Either way it works. Right. B prime, B not, right, or not B. So the probability of the complement of A is 1 minus the probability of A, right? So if I tell you that the probability that we'll end class early is 15%, Because what does that mean? What's the probability that we won't end at class early? It's not good, right? Well, it's high, but it's not good. So, right, so we understand complements and we use them already. And so it's on your formula sheet. Right. So I'll highlight it in pink. But the only new concept here is the probability notation and maybe the superscript C to denote that it's the opposite, right? But besides that, there's nothing really crazy going on here. Let's talk about independent events. In the back. So let's talk about independent events. So again, it's one of those things that we know, we understand, but we need to stretch it into probabilities, right? And so two events are independent if the outcome of one does not depend on the other. It's easier to think about non-independent events, right? Things like the weather, for example, right? And I think I use this example, right? If we know the weather today and we knew the weather yesterday, right? I can kind of know the weather for tomorrow, right? Because they're not independent events. Flipping a coin, though, are independent events because the outcome of my next flip does not depend on my previous flip, right? And so if the outcome of one depends on the outcome of another, then they're not independent. And so how we use this, right? And there's some examples here, right? Stocks. So the stock market, it just kind of follows each other. It moves, right? But just kind of incrementally following each other each day, each hour, whatever. Weather, same thing, right? We know the weather changes slowly over time, right? But from day to day, we're not expecting huge changes. Even diseases, right? We talk about, well, if you're living with someone who's sick, you're more likely to get sick, right? Than someone who's not living with someone who's sick, for example. Even drawing cards without replacement, right? So I've got a deck of cards here. I pull my first card and I tell you my first card is a red card, right? Now the probability of drawing another red card is slightly less than drawing a black card because I've got all my black cards in the deck still, right? So if I'm not putting the cards back in, which can happen, right? Draw a card, right? So then I'm drawing without replacement, and so then these probabilities, right, depend on what happened previously. How we use this is that if A and B are independent, then this statement is true. So what we need to check to see if two things are independent is we need to know the probability of A and B, as well as the probability of A and the probability of B. So then if we multiply the probability of A and B together, and we get the same as the probability of A and B, then we can say they're independent. Okay? We don't want to use it the other way around, right? So if I'm looking for the probability of A and B, I can't just multiply the probability of A times the probability of B, because then I'm assuming that they're independent, right? So we can't use it the other way, but we can use it to check if things are independent. And this is on your formula sheet. And I'll use a smaller pencil size here. And I'll write, given the probability, the probability of A and B, the probability of A and the probability of B, we can determine if A and B are independent. Yeah. Sorry, just seeing how much space I have. We can determine if A and B are independent by calculating the probability of A and B. Does it equal the probability of A times the probability of B? Yeah. So this is only if they're independent events, right? In the next section, we'll talk about conditional probabilities, meaning these things are not independent anymore. And then we'll be able to have a formula for the probability of A and B, right? But just remembering that this formula for the probability of A and B on your formula sheet is only true if they're independent, right? So if you don't know if they're independent, right, then you can't use this formula. Right? And just like that, I guess I'm out of time, huh? But we had a fun example coming up. We'll start on the example next day. Can't believe it. I will see you guys on Monday. Bye, Sage.